Today we're starting chapter 16. Hopefully you've already saw the video on the Khan Academy about light fundamentals. Our goal today is to recognize that light's an electromagnetic wave and know the wavelength range, define a ray, and then state the speed of light and solve different problems with that. I'd like you to do to start with is open your book to page 372, pause the video here, and see if you can figure out what's going on with that picture. We'll let you pause it a second and think about those colors. Some people might say, well, it's just drawn on the back wall or it's photoshopped or whatever, but you can actually make different color shadows, and we're going to show you how later on in the chapter. Hopefully we can figure this out as we go. So what are some different facts of light? Well, the only time or reason we see objects is because they reflect or emit light. Light bulbs emit light. The sun emits light. The moon does not. The reason we see the moon is because it reflects light. If you've ever been in a cave, way in the bottom where they turn off all the lights, you can't even see your hand 6 inches away from your face. You need some light to reflect back to your eyes so we can see things. So what is light? Well, we're going to define light simply as the range of frequencies of the electromagnetic spectrum that stimulates the retina. And the visible region of the electromagnetic spectrum that we can actually see happens between 400 nanometers and 700 nanometers. Any other type of light we cannot see. There are more regions in the spectrum. Obviously, we learned a whole lot of the spectrum in chemistry, spectra, but this is the only part of it that we can actually see. This would be the whole electromagnetic spectrum. You've got radio waves and microwaves. We use them all the time to warm our food. Radio waves obviously are present. We turn the radio on, you can hear it. Infrared, you can use to see things that give off heat. This is the only part of the spectrum that we can actually see, the visible region. And then it goes on to ultraviolet, X-rays, gamma rays. Notice as you go from left to right, the energy increases. We know that gamma rays and X-rays have a lot more energy than radio waves. And we also know that the frequency increases. So energy is directly related to frequency. But again, a small part of the spectrum is actually visible to us. We're going to assume that light travels in straight lines. We're just going to call them rays. And ray optics is simply the study of the travel of light using rays. So we will do this. We'll have a rays going towards a medium, and we'll see how it reflects. We'll see how it refracts when it goes into a medium. We can see how it bends around corners or diffracts later on. We'll use light rays to make those observations. Now, all we want to do today is just talk about how the speed of light was discovered. The first guy that worked with it was Galileo, and his experiment was simply to put 2 lanterns on mountaintops. And you have synchronized watches, so as soon as I open up my lantern, we're going to set a certain time. You time how long it takes for you to see on your mountain. So we're miles and miles and miles away. And you can imagine back when Galileo did this experiment, the technology wasn't so great. So as soon as I opened up my lantern at the time specified, almost instantaneously, or pretty much instantaneously, the guy on the other mountain would see it. So the only conclusion they came up with was the speed of light is too fast to measure. The next guy was Romer. In the 1600s, he measured the time when Io, which is a moon of Jupiter, emerged from Jupiter's shadow. So as soon as you can start seeing it, measure how long until you get to the end of the planet, or the outer edge. And he observed that the time varied whether the Earth was moving toward or away from Jupiter. So if you're going towards Jupiter, that distance is decreasing. Going away from Jupiter, obviously the distance is increasing. And there's a measured difference in time, whichever, based on the direction we were going. So we still couldn't figure out how fast light was, but the conclusion was the speed of light is a finite number. There definitely is a value for the speed of light. They just didn't have the technology to figure that out yet. And then, around 1900, Michelson performed an experiment where, kind of the same idea with California mountaintops, he set up a vacuum tube 35 kilometers apart, and that'd be like going from here to Haywarden. Sent a laser beam through the tube. When it hit the other end, there's a mirror, so it reflected back, so you're really getting twice the distance. And he was able to conclude that the speed of a light was around 2.997996 times 10 to the 8th meters per second, which is very, very close to what we actually believe it to be now, which is 2.99792458 times 10 to the 8th meters per second. And you don't have to remember 9 significant digits. For most of our work, c, or the speed of light, if we just round that to 3 times 10 to the 8th meters per second, that would be good. So let's figure out, do an example here of how long it took for this light to travel in his experiment down to the end of that tube and back. Well, that tube, we said, was 35 kilometers, and there's a mirror on this end, and he sends the laser beam down here, or the light ray this way, and it bounces back. The total distance the light traveled would be 70 kilometers, or 70,000 meters. We know the speed of light is roughly 3 times 10 to the 8th meters per second, so we should very easily be able to solve for the amount of time it took in his experiment. I would just use my velocity of distance over time equation. And in this case, the velocity is the speed of light, so 3 times 10 to the 8th meters per second equals 70,000 meters divided by the time. So, when you calculate that out, take your 70,000 divided by 3 times 10 to the 8th meters per second, the time it would have taken is 2.3 times 10 to the negative 4th seconds, or 0.00023 seconds. So hopefully you've watched this video and the introductory to light on the con video for today, and we will see you tomorrow.